Hello everyone. So today we would be seeing a PowerPoint presentation on the topic addition of a branch or a link to a bus impedance matrix. So what exactly it is? It's also called as the Z-bus building algorithm in the subject power system analysis and dynamics. So we'll see the contents first. I'll use the laser pointer. Yeah. The contents, first we'll see some introduction and terminology, then we'll see four types of modifications, and then a few references. We'll also study about an example that is present for the modification. Now, introduction. This is a step-by-step programmable technique. It proceeds branch by branch. It is not a simultaneous technique or a very hectic technique that everything is happening all at once, but a step-by-step technique, so it is very easy to interpret and understand. And it is very advantageous as complete rebuilding is not required in the system. So this is the most basic diagram of our Z-bus building algorithm. The Z-bus old, which means our impedance matrix, initial old impedance matrix, we add a branch impedance ZB to it. Between two nodes, a branch or a link can be added, and then it gets converted into the new Z impedance, that is the new Z-bus matrix. How it is being made? This new matrix has different forms as different types of modifications are carried out. We will see how is it made. Some terminology is I and J are the old buses, R is the reference bus, K is the new bus. Now, what is addition of a branch and addition of a link? First, we see what a branch means. A branch means when a new bus is connected to an already existing bus. That is a branch. And what is a link? A link is the link between two old buses, which means two buses which already exist in partial network. That is known as a link. We'll understand the concept of branch and link further when we proceed with the example. Now we'll first see the type 1 modification, in which we have this basic diagram in which I and J are the old buses, and 1N and all these are also the buses. I and J are the old buses. K is the new bus that has been added, and R is the reference bus. An impedance is added between the new bus and the reference bus, ZB. And then we perform KVL, KCL to find out the Z-bus matrix, which would be changed. BK is equal to ZBIK, the voltage drop across this impedance. Then ZKI and ZIK would be 0. Why? Because there is no connection between I and kth bus. So ZKI and ZIK is 0. Simple. And ZKK equals to ZB. Now the new Z-bus impedance matrix is equal to the old matrix, a new column which is completely 0 in this type of modification, a row which is 0 in type 1 modification, and a last column term and a last term, corner term, which is ZB. So this row and column and this corner term are included in this type 1 modification. In the further modifications, we'll see how these vary. Only the difference is that only those vary. Now, type 2 modification. This is the basic diagram of type 2 modification. J is the old bus, K is the new bus, and ZB is added between old bus and new bus. In type 1 modification, we added an element between reference bus and new bus. Now it is existing bus and new bus. Okay, existing bus and new bus K. So this is a KVL that has been applied. VK, that is voltage at K, is equal to the KVL plus VJ, and then this is expanded as per the KVL rules. Then rearranging the terms, we get this, and writing this in the matrix form, we get Z bus old, this new column and row. This new column, the terms are Z1J, Z2J, up to ZNJ, where N represents the N bus network, total number of buses in our system, that is ZNJ. Similarly, ZJ1, ZJ2 up till ZJN. And the last corner term is ZJJ plus ZB. This is the type 2 modification. Now comes the type 3 modification, in which the simplest type of modification is done. A ZB element is added between reference bus and existing bus. There is no new bus K. Here, no K bus is present. So ZB connects an old bus J to a reference bus R, and the Z bus new is equals to the Z bus old minus 1 upon a denominator term, which is the ZJJ impedance of J, plus this impedance multiplied by a column vector into a row vector. Now this is the modification that we require to add in the old matrix to form the new matrix. So this is the matrix representation of this formula. This is the voltage. This is the new Z bus, that is Z bus old, new column, new row in this last term. This is a like same modification like type 2 modification. Only the difference is that this Vk term is 0 here. Vk equals to 0 because no K bus is present here. No new bus K is present. So this was the type 3 modification. Now we see the type 4 modification, in which the ZB is added between two old buses I and J. This is somewhat complex modification, but we'll see that in the matrix it becomes easy to remember. So between two old buses, we add a ZB, then we perform KVL, eliminating IK, we get this equation, in which this also contains 1 upon the denominator and row vector and column vector. So the modification is this comes the column vector, this comes the row vector. This is the corner term, which is also called as LL term. This type 4 modification is basically the modification when a link is added between two existing buses. We will see what this statement means in the example further on. But when a link is added, this type of modification is performed, and further on, this row, this column and this row is reduced to a matrix of the dimension of Z bus old. We'll see how. This is the example of a Z bus building algorithm. So this is a single line diagram of a power system that we have been given initially, which contains of 4 nodes. Node number 1, node 2, node 3, and node 4. These 4 nodes are interconnected with 7 branches and links within each other. This is the reference node 0, and these are all the impedances. Now this can be represented as graph or tree of the network, which is easier in interpretation. So from reference node, we have first branch to first node, then the second node, third node, fourth node, and these all branches are named. Total 7 branches or links are present. The green line shows the branches, that is 1, 2, 4, and 5. Total 4 branches are present, and the links are 3, 6, and 7. These 3 are the red dotted lines are links. We will further on see what a branch and a link has effect on the Z-bus matrix. So the step 1 is, okay, now in the 4 modifications that we saw earlier, we saw that what we did was there was an existing power system in which we added a particular branch or a particular impedance between two nodes. Already the system was existing, so we just added a row or a column. In this, the same method will be followed, but here we will start from the reference node 0, and then we'll start building the whole system that we saw in this diagram, this tree. We have to start building starting from this reference node 0. So first we form a node 1. Between 0 and 1, we have an impedance Z10 with J0.1 ohms as the impedance. And this branch is being added. So the Z-bus matrix will be Z10, which is a 1 cross 1 matrix, and the value is J0.1. This is a 1 cross 1 matrix. So now step 2 comes. In step 2, what have we done is that just like we added new node 1 to reference node 0, in this we add a new node 2 to the reference node 0, and this is named as the branch number 2. So like we saw in the modification 1, when we add a new node to the reference node, what we get is that a 0 column, a 0 row, and a last term which equals to the impedance between these two nodes, which is Z20, Z20. So this is the 2 cross 2 matrix that we get. As two branches are present, so 2 cross 2 matrix verified. Now comes the step number 3. What we do in step number 3 is that we connect node number 2 and node number 1 with a link. So here carefully, this is a link. In before two steps, step 1 and step 2, what we did was we added this branch and this branch. But in step 3, we add a link. So what does this link do? First, we perform the modification in the Z-bus matrix. This is a temporary Z-bus matrix. We'll understand it slowly. Temporary Z-bus matrix in which this modification is done according to the modification number 3 that we saw before. This differences in the last term is ZLL, which equates to this complete summation. So we'll put in the values, and this is a 3 cross 3 matrix, but this is a temporary matrix, Z-bus temp. Next, a new row and column is eliminated. This red column and row is eliminated to restore the size of this. So using this subtraction formula, we will convert this temporary matrix into the new matrix, which is 2 cross 2 form. So we see that there are two branches and one link. So one thing that we can conclude is that the branches change the dimensions of the matrix or the size of the matrix, and the link does not change the size of the matrix but the values of the terms inside the matrix. We will also see these further in every type of modification that we are doing. Step number 4. Step 4 includes the addition of a branch again between node number 2 and 3, branch number 4. So this branch is being added, a new node and existing node. So this is a modification, new column, new row with the specific elements of the impedances, and this is the final corner element. So one row and one column is added, and this matrix becomes a 3 cross 3 matrix. See, 1, 2, and 3 branches are there. 3 cross 3 matrix. Step 5. Element 5, that is branch number 5, is added between existing node 3 and new node 4. Just like we did in the previous step 4, we'll add a column, a row, and then this matrix will become 4 cross 4 matrix. 4 cross 4 matrix means there are total 4 branches, 1, 2, 3, and 4. This is not counted as this is a link. Now in step number 6, what we do? We connect a link between the node number 4 and node number 1. This link, so now we know that when we connect a link, the size of the matrix does not change. We first find out the temporary matrix using the formula. Then this temporary matrix has its column and row removed, and the values are changed according to this formula. And so we get a new matrix which is 4 cross 4. 4 cross 4 matrix. Now the step 7, final step, is coming, in which we add a link between two existing nodes 2 and 4, just like in step 6. We will find the temporary Z-bus matrix. In that temporary Z-bus matrix, we'll put in the values, and then we'll reduce it to a 4 cross 4 matrix. Now we can verify that this is a 4 cross 4 matrix, which means that there are 1, 2, 3, 4 branches and 3 links. So 4 branches means 4 cross 4 matrix. As can be seen that the final Z-bus is a 4 cross 4 matrix, as the network has 4 nodes and a reference node. There are 7 elements in the network. Now till now we have seen that we have added a link or a branch to every node between two nodes, and we have formed this matrix. We have formed this complete system, but we don't know that how we do remove a particular link or a particular branch. To remove that, we can't directly subtract the terms from the matrix. We have to go on step by step. So what we can do, if suppose that we need to remove this branch number, this link number 7 between node 2 and 4, and this link has the impedance of J0.4. So we add another link between these two, which is link number 8, and we put the impedance of that link to be minus J0.4, that is negative of the 7th link. If we do this, then these two impedances cancel out, and hence nothing is present in between node number 2 and 4. So we'll try this way. We'll see that what happens. So now a link is added with minus j0.4. So we'll again perform the modification for the link, modification 4. Temporary matrix we'll find. After that, substituting the values, finding ZLL, and then we will reduce the matrix into 4 cross 4 matrix. Now this matrix we can compare with the previous step number 6, that this matrix and the matrix in step 6 which was obtained before the element 7 was added, that is link 7 was added, are the same. So it is proved that yes, the matrices can be reduced, any link can be removed by adding a negative impedance along the link, a new link. So we have formed the complete system by step-by-step process of adding a link and a branch between nodes and following various modifications. The references used in the PowerPoint presentation are Modern System Analysis, Modern Power System Analysis by D.P. Kothari and I.J. Nagraj. Thank you, everyone.